Hello everyone, welcome to ISAT330 Sustainable Manufacturing Systems. This is the lecture 10, also the last lecture of this course, Sustainable Manufacturing. Alright, so today we're going to talk about first a little bit of theory about sustainable manufacturing, what is sustainability, life cycle thinking, and life cycle engineering, and then system thinking, how system thinking can be integrated into sustainable manufacturing. Next, so after you learn what is sustainable manufacturing and how to practice that in manufacturing systems. So lastly, we're going to discuss something about social sustainability. All right, first, sustainability. When we're talking about sustainability, there are many different definitions. Well, the definition we gonna use here is we're mainly looking at we are looking at sustainability from three different aspects: right? Economic, environmental, and social aspects of sustainability. So when we're talking about economic sustainability, mainly we are looking at improving efficiency, looking at how the profit, that economic profit they can be made from manufacturing systems. While environmental will be related to both the environment that will be healthy to the employees and also to the society, to the earth. Then lastly, will be the social responsibility of manufacturing system. Society's aspect, the social responsibility to environment, related to safety and health of employees, as well as some other metrics, for example, local employment, child labor, human rights, a bunch of other metrics you can measure social sustainability. And there are different ways we can look at it. Sometimes people look at sustainability there are three pillars: economic, environmental, and social. These are the separate pillars. Well, sometimes when you'll see people are looking at sustainability as those kind of overlapped area between society, economic, and the environment. So the area here will be the one that we want about sustainable manufacturing, because we want, again, all both the economic and environmental and social sustainability. Well, another aspect will be another way to look at sustainability is will be the circles here. The outside circle will be the environment. So basically, we're saying that we are actually all the business activities, all our manufacturing activities are happening on this earth. So that's why the environment will be the first. Make sure we do not hurt our environment, that because eventually we'll have to pay for that. Next one will be the society. So because our business within the society, we have to comply with societal rules, so that all the activities will be conformed with regulations and laws. And lastly is the economic. So that is our business activities here. All right, then now let's look at what is the how do we calculate the impact on environment. So there's the ISAT equation, or another way is the master's equation. So basically, both of the equations are looking at how to calculate the impact on this Earth environment. So the equation equals to the population times the affluence times technology. So affluence can be calculated by GDP per capita, and technology can be calculated by impact per dollar of GDP. Well, looking at those three variables, we know that the population, from history perspective, population has been growing up over the human history. Same with the affluence, or the GDP per capita. So the only variable we can work on is the technology. So how can we reduce the impact per dollar of GDP, so that the impact on the environment can be reduced or be slowed. So this is the ISAT equation. Please keep in mind about this equation because it has been widely used in environmental engineering and also in sustainable manufacturing. All right. Next is the life cycle thinking. We are talking about how do we protect the environment, how the activities, business activities affect the environment. We have to look at how the material flows over its life cycle. So that's why we need to look at this life cycle thinking. There's a video I would like you to watch. So make sure you click this video, this link, and then watch the video to learn about what is life cycle thinking and how life cycle thinking will help you to identify opportunities to improve sustainability. And we are looking at the whole product life cycle. So mainly there are several stages, like material processing, where raw material will be processed into manufacturing ready for manufacturing raw materials. For example, steel sheets or some other materials. While manufacturing will be making the products for customers, and then there's a distribution to transport the products to the customers or to the markets, and then customers will use it, and then eventually will be either disposed to landfill, and then after years, it will be transported, be extracted from the earth. That'll be the material extraction. For example, mining, right? And or the product after use can be recycled or can be remanufactured, or it can be reused by another customer, or it's just you can be maintained that in for longer product life. So this is the product life cycle. A lot of times, if you look at this product life cycle, when we're talking about sustainable manufacturing, really we're looking at the materials and how the energy actually consumes over the life cycle. For example, a cars, or a fridge, or a chiller, right? So those kind of products are mostly it's energy consuming products. That the most environmental impact is not from the manufacturer, it's not from the materials, it's actually from the use stage, right? Because during the use you have to consume gas, you have to consume energy or electricity. So that later we're going to look at one example. You can see how the use stage actually contribute the most environmental impact over its product life cycle. So that's why when we learn that, we have that result, then we can start to find out what are the ways to reduce the overall life cycle environmental impact by improving the product design. So this is how the life cycle thinking will assist you for improving sustainability. All right, next one is the system thinking. So we learn about life cycle thinking. There's also system thinking because all the components of sustainability and also manufacturing system are related. Right, are interrelated, so they are not separate. So they all have consequences and also have feedbacks. And so the way I look at a system is it's a perceived whole in which elements are interconnected and have a purpose in its given context. And so you can see that the system, there are several different components. Then these are system components. You can see that the one are going to affect another. So we have feedback loops or consequences. So this is how system works here. But system is not just those components. System also has a purpose and also has boundaries. Right? Also has boundaries. Another thing, a system also have a context. For example, in a class, right? This is the course of ISAT330, right? We have a purpose. The purpose, we're going to talk about how the production planning and control are managed in manufacturing systems, or how the sustainability actually practiced in manufacturing systems. So this is the purpose, right? The purpose is I want you to learn that. Well, there are also boundaries. Boundaries means I'm not going to teach you music. I'm not going to teach you psychology or a lot of other things because I want to, keep this boundary and I only teach you the manufacturing things, right? Maybe going to expand a little bit, but still that's within. That's because of the purpose. The purpose defines, right? The purpose defines how can I draw the boundary, right? How can I draw the boundary? Well, if I know the purpose, I know the boundary, I can define what are the variables, right? What are the variables that need to be included in this system? And then figure out what are interactions between all these system components. Well, another thing is the context, right? Another thing, the context. The context means what is it mainly about? Like this is a manufacturing course, so this is not a music course, right? It's not a music course. And also, so how do you differentiate this context and the boundaries? So the boundaries can be interpreted as, for example, in this course, there are a lot of manufacturing things, right? I'm going to talk about scheduling, talk about layout, but in scheduling there are a lot of really complex algorithms that I'm not able to discuss that in this course because the scheduling itself will be the core course, right? I can only introduce you something simple algorithm so that you can get an idea about it. So that's a depth I can get into, and that's the boundary of this course. Yeah. If the purpose changes, right? If the purpose changes, say, oh, this course is gonna be mainly about scheduling, then I'm probably gonna change my boundary and say I put a lot of scheduling algorithms, put a lot of calculations, put a lot of coding and in it, so you get a better understanding about scheduling. But because of the purpose is different, that's why this how the boundary works. Well, the context will be, this is totally different knowledge, like music versus manufacturing, right? Or psychology or philosophy versus manufacturing. Well, another aspect of this whole system is the analyst's view, or Weltanschauung. So Weltanschauung is a German word for worldview, so mean how people look at it. Give you an example. Think about James Madison University. So maybe 3 years ago, or maybe 4 years ago, when your first time come to Harrisonburg or come to the JMU, you had a view on how you look at JMU, right? Probably everything's new, everything's excited, and that kind of view probably will be different with the one how you look at JMU now, because you get more familiar with it, you got a chance to interact with the students, with the professors, then you got different stories. Now come back and look at JMU again. You will see it differently. So that's the Weltanschauung or the analyst's view. Even though it's the same university, it's the same system, well, people can have a different view over time, right? Also, different people have their own views on the same thing. So this is how you look at a system. And system thinking is what? System thinking is a holistic approach to learn about the process and solving problems. So system thinking is trying to understand how these interactions work, how and what causes the performance change by analyzing the whole system, by understanding it. So when a problem happens, the first thing you have to think about is not to solve the problem. When the problem happens, the first thing you need to do is trying to understand what's going on and find out what really happened. If you do not understand how the system works, it probably won't be able to give a very good solution. Usually what happens is, when we got a problem, yes, we give a solution and solve it. And then the solution you give actually going to cause some other problems, right? So sometimes we call it unintended or consequences, right? That's why it happens. But in system thinking, we want to give a more comprehensive solution based on an understanding of the whole system and how the problem, how it works related to the problem. All right, sustainable manufacturing. So, sustainable manufacturing is, I gave a definition years ago. It's a set of system activities for the creation and provision of manufactured products that balance benefits for ecological systems, social system, and economic systems. So there are some of the terms, I want you to focus on is, creation, provision, and all balanced benefits. It's easy to understand the first two. Then the balanced benefits means really you want to balance or find optimize or equilibrium state that all the three pillars of sustainability can benefit, right? Of course, there has to be positive benefits to both to all the economic, environmental, and social sustainability. So that's why it's called balanced. Instead of sacrifice one thing and just to achieve the maximum benefit from of another thing. So that's sustainable manufacturing system. And also when we are looking at this system manufacturing problems, you also have to think about it as a system. Right? Think about it as a system. What is the goal? Right? What are the interconnections? And what's the purpose, and what's the boundary, and how the interactions work, right? What are the metrics for measuring the performance? So this is sustainable manufacturing, and well, in terms of how to practice sustainable manufacturing, there are many different tools, and one thing is. One important category of tools will be analytic tools. So analytic tools include environmental sustainability measurement or assessment, economic sustainability assessment, and also social sustainability assessment. So today we're gonna focus on life cycle assessment, which is part of the environmental sustainability assessment. Well, for economic sustainability, basically we already talked about that in engineering economics, right? There are cost benefit analysis, life cycle costing, all the other different calculations related to money. And for social sustainability, also going to discuss that after we discuss environmental sustainability. All right, within the category of environmental sustainability analytic tools, there are life cycle assessment, economic input and output life cycle assessment, hybrid LCA, and material flow analysis. So in this course, primarily going to focus on life cycle assessment. So what is LCA? A little bit history about it. LCA started from 1950 or 60s when Coca-Cola started to measure the environmental impact or the GHG emissions out of a can of Coke, right? And then did some of the calculations about the emissions. Use the function unit as 1 can of Coke and how much emission going to generate. So that's the start of how people started to do life cycle assessment. Formally, actually the life cycle assessment was defined by I think ISO in 1996. And it gives a formal definition is that it's a compilation and evaluation of inputs and outputs and the potential environmental impacts of product systems throughout its life cycle. Right? So inputs and outputs, right, is the evaluation and compilation of inputs and outputs potential environmental impacts of a product system throughout its life cycle. Remember, it's a life cycle. There are stages, right? There are stages. For each stage, there's input and output, right? There are input and output. It can be materials, it can be energy, and something else. So we analyze each stage, what are the input and output, and how they're gonna relate to the environmental impact. And then we compare all this information and analyze it and find out this whole life cycle of emissions or environmental impact and compare that to have a better understanding. Right? So this is the life cycle assessment. And for ISO standards, it has the 14040 series. It defines, what are the principles and framework about how to conduct life cycle assessment. Mainly include, first stages, goal and scope definition, life cycle inventory, impact assessment, and interpretation. So you can go through those standards. You do not need to remember each of the each of the ISO standards numbers, but you need to know the 14,000 series, 14,040 series, right? These are the life cycle assessment ISO standards because it has been used a lot in literature and in calculations. All right, the framework for LCA includes 4 stages. First, goal and scope definition. Second, life cycle inventory or inventory analysis. Third, impact assessment. And the last is interpretation. I'm going to go through one by one. So first, what is goal and scope definition? So the purpose of having goal and scope definition is to define, what is the application of the study, why do you want to conduct the study, and also who will be benefiting from your study result. And also in the goal and scope definition, you need to define what is the functional unit, right? So remember, the functional unit is defined as what? It's not the functional unit does not mean it's centimeters or it is dollar or it is kilometers or what. That's not a functional unit in LCA. Functional unit means what is your environmental impact unit, right? It's based on what? So is it your functional units will be GHG emissions per unit of can, right? So if I want to study a can of Coke, okay, I'm going to evaluate. My results will be based on for 1 can of Coke, how much GHG emissions are generated. I'm not going to looking at whole day's production of can of Coke. I'm only looking at 1 can of Coke, how much GHG emission. And during the calculation, I want to convert all the information related to only 1 can, all right? For example, 1 can's weight, right? Also 1 can's, energy consumption. So all these, will be based on the 1 can. So this is the functional unit, right? This is the functional unit. Right? This is not, it's not the traditional, unit concept. Same, if I want to evaluate, or cars, right? You can evaluate, for example, GHG emissions per what? You can say per car or per what? Per kilometers or per mile a travels, right? So this is how you can if it is GHG emission per car, then we're probably gonna look at during this whole life cycle, for each car I make, I purchase or I made over the whole life cycle, how much emission is generated. So this is GHG emission per car. Well, it is for kilometers. It means how much GHG emissions it will generate when the car I'm going to analyze when it travels 1 kilometers, right? When it travels 1 kilometers. So what is GHG emission? And this GHG emission has to be the what? Has to be the whole life cycles GHG emission, right? Then what you're gonna do is you're gonna look at how many kilometers you can drive over the entire life cycle of the car. And then how much GHG emissions will be generated over the entire life cycle of the car. And then you find out what is GHG emission per kilometers. So this is a different functional unit. This is called different functional unit. Right? And when you are selecting functional unit, you have to be very careful because sometimes it's comparable, sometimes it's not comparable. For example, a car. Which one do you want to choose? Choose GG emission per car or GG emission per kilometers, right? If you choose GG emission per car, then you're thinking for different models, right? If a car has 15 years life, another car has 20 years life, another car has maybe only 5 years life. How can you compare GG emissions based on that? Is this still reasonable, right? So that's the. If you think that's not reasonable, then you have to think about what functional units I choose that be more reasonable, so all the different cars can be comparable. Maybe GG emission per kilometers, or maybe something else. So that's why selecting functional unit is a very important task, or actually the most important task in GG in Go and Scope definition here. And another aspect will be in Go and Scope definition, and very important aspect is system boundary. So system boundary means what should be included in your analysis. Now remember, in system thinking, we talk about the purpose that actually determines the boundary, right? So if you know the purpose of the analysis, you should be able to identify what is your system boundary, what should be included and what should not be included, right? So here there are some common terms or common ways of setting system boundaries. First, when we determine system boundary, we determine a clear starting point and an ending point, and what is included and neglected in our analysis, and also materials and energy inputs into processes. So common ways will be, if it is a product, usually we call it cradle to gate, gate to gate, and cradle to grave. And if it is fuse, when I'm talking about fuse, we call it well to wheel, well to tank, and well to wheel, tank to wheel. So from these words, you can tell what it means. But I'm gonna start to look at a graph. So if it is a gate to gate, the gate means the manufacturing company's door. That's the gate, right? All right, that's the gate. So gate to gate means from the door that is materials get in, to the gate that is product coming out, right? From the entrance of the factory to the exit of the car, exit gate of the factory. So this is gate to gate. And if it is cradle to gate, means from the raw materials extracted, right? And here it will be being processed and then production. So this is a cradle to gate, right? Cradle to gate. It's not just the manufacturing itself. We're also going to look at the prior stages, right? How the material is actually extracted from the earth and how it is prepared, and then comes to the factory, right? So this is the cradle to gate. Well, another one is the cradle to grave. Cradle to grave includes not only the extracted material preparation, production, but also the utilization and disposal, right? The use stage on the transport station, use stage, and also the disposal. Disposal means it's end of life of this. That's why we call it the grave, cradle to grave. Another term, it will be the cradle to cradle. So cradle to cradle means it actually can come back, right? Gonna come back to the raw resources. All right. So the next next stage will be phase 2. It is life cycle inventory. So life cycle inventory basically is creating an inventory of inputs and outputs within defined system boundary, right? For example, all right, when we have different stages like raw material extraction, for example, all right, we have raw material extraction. Then we're gonna look at what materials, equipment, right, energy, equipment will be used in this whole process, right? Material, can be, for example, if you're extracting fuels, then you probably want to inject carbon dioxide or some auxiliary material or water to help this process, right? So the auxiliary materials going to use. Equipment, what much equipment going to use? You have trucks, some other equipment, machines, energy. What kind of energy you use, right? The fuels or electricity or something else. And all these, right? You have to quantify them. Think of how much material I use for the functional unit. Remember, now you have to convert everything to the functional unit, right? What is material, what is energy, what is equipment, or the other, will be used for during this process. During this process will be the final product or the result, right? Output. And so this is then you come up with what? You come up with a table. You come up with a table to show how much energy, how much material, how much equipment, what is it being used for this process, based on function unit. And this information is very important because this data will be converted to the environmental impact later during the phase 3 or stage 3 of LCA. But currently, let's just look at life cycle inventory, the second stage, right? It's data collection, right? It's data collection. So data collection is very important stage because a lot of times you probably won't be able to get the very accurate data, right? In this case, you probably have to make some assumptions, right? You might have to make some assumptions, or based on literature data, right? That's based on information that you cannot get the actual data from the actual system. If you can, then that's great. You just go and record the data and get it. If not, find some literature to do some estimation. So that's a data collection. It has to be related to the functional unit, right? It has to be related to the functional unit. Material use, what material be used, energy consumption, different resources of that. And forms of LCA can be tables, can be flowcharts, but as usually it's tables, right? Usually it's tables. You want to make sure that you know the information and what is the value, quantitative value, and also what is the unit, right? Then the next stage will be the impact assessment. So the purpose of the impact assessment is want to convert, right, life cycle inventory, the data you collected to calculate the environmental impact. Convert for example, if I know how much energy I use, then I'm going to convert that kind of energy data to environmental impact, how much GHG emissions generated, right? So that's impact assessment. So there are different ways you can calculate, and actually you got a different database as well. For example, also there are ways, how do you categorize the environmental impact, because there are many different different impacts. Like GHG emission is one impact. Water use is another impact, right? Also, the land depletion is also another impact. Also, there are a bunch of other things. And in terms of how to categorize them, how to group them, and how to evaluate the overall environmental impact, people invented different methods and ways. Common ones will be recipe method, the tracing method, right? And some common impact categories will be GHG emissions and global warming potential. And the calculation is to be based on a life cycle inventory. And in terms of the tools and softwares, there are many different softwares. Some are free, some are not free. So OpenLCA is free, and I think Gabi is free for education. And there are SimaPro is more for professional, and it's not free. And the GRID is developed by the Argonne National Lab, but the GRID is mainly for transportation sectors. For example, a car, vehicles, right, and ships or trains, trucks, those kind of things. You will get very good information from the GRID models. Also, there are some like GH Genius, sustainable minds and eco audit. So sustainable minds and eco audit, these are more developed for education purposes. In terms of database, the database means, for example, if I database means people have already calculated a certain subcomponent or sometimes even whole component, right, of impact for you already, so you can directly use it, right? For example, if I want to evaluate the environmental impact of a manufacturing a car, right? Well, when you are looking at evaluating a manufacturing a car, the one component is you have to look at what is the materials and facilities you get into it, right? About the manufacturing a car, you involve what? Raw materials, right? Raw materials can be, there will be glass, there will be steel, aluminum, a bunch of other materials, and also what? And also energy, right? You need energy consumptions, and also what you need tools and equipment. What else? There are also facility. Facility will be, for example, the whole building of the plant, right? All this concrete, right? Believe it or not, that's part of the environmental impact you have to do in order to make a car. Because if there's no land, no plant, how can you make a car? So that's why this plant or buildings also need to be counted in the manufacturing of a car. But sometimes say, okay, I don't know how much environmental impact for building a plant, right? So this is when a database will help you, because someone has already studied from literature, or some professors or some agency that studied that, right? If I want to build a manufacturing plant, what is the general GHG emissions actually going to cost resulted from this, right? That can be a separate study, right? Just trying to look at the building a manufacturing plant. Then, in this case, you can directly use that result into your analysis of manufacturing a car. So that is how the software and the database will help you do that, right? Of course, you need to define the functional unit, right? You define well the functional unit. Then they will convert that kind of emission to your functional unit. So this is how you use software and database to do that. Well, it's not always you should use the database. The database will help the software, but sometimes you can also manually calculate how much you make GHG emissions, as long as you know the emission factors. For example, if I know I for using the 1 kilowatt of electricity, I know how much GHG emissions will be generated. Then you just look at, okay, how many kilowatts of energy you used. Then you can convert that to how much emission you generated. That's emission factors. All right, for different impact categories, these are the common ones like global warming potential, ozone depletion, acidification, eutrophication, water use, and land use. You can see these are different data, and also the factors, how to do that, how to calculate that. And also examples of data you can for measuring of the global warming potential. There will be carbon dioxide about these, right? And then the last stage will be interpretation. So interpretation means how do you evaluate your study, right? And also how do you evaluate the quality of your results. First, how to evaluate your study, because you probably made a lot of assumptions, right? Made a lot of assumptions in your data collection, in your also in your maybe boundary drawing. Then you have to take that into consideration about your result, because all this information will actually will affect your result. right? All these uncertainties will affect the result. So that's why in interpretation, a lot of times people are going to conduct a sensitivity analysis and uncertainty analysis. Right? So the sensitivity analysis means it determines which independent variable have the largest impact or effect on the desired impact, right? Same, for example, if we are looking at a car, right? A car's environmental impact. All right, I'm probably gonna try if I use more steel, then how much it's gonna affect the final environmental impact result, right? If I want to measure the GHG emissions per car, or per kilometers, then if I see that I only increase a little bit, let's say I increase 5% of steel use, it actually does not really affect much of the final result. Means increasing the use of steel actually does not have a really high sensitivity on the result. The result, or in other way, the result does not have the really sensitive to the steel use. On the other hand, say if I increase the efficiency of the fuel use, right, only by maybe only 1%, then it actually had a really huge difference on the life cycle environmental, GHG emissions result. Then in this case, we can say that the result, the environmental impact result, is very sensitive to the fuel efficiency of the car, right? So that's how you sensitivity analysis and try different variables, and then look at how they will affect the result, and trying to determine which factors or which variables are actually important to the final result. Yeah, you can vary only one independent parameter at a time, and also the variable causing the largest change has the most impact on the result. All right, now let's look at one example, the Honda Civic car. It's a case study that was conducted some years ago. So basically, first stage is goal and scope definition. We define what is the goal of the study, right? We want to determine the GHG emissions. Now you determine the GHG emissions. In this study, you are not going to look at the ozone depletion or some other metrics about environmental impact. I only look at the GHG emissions and over a lifetime of the car, right? Over a lifetime of the car. And also you need to define what is that, right? It's this model of the car, right? There are many Honda cars. I'm gonna look at this model of the car. And also next will be functional unit. Now that's why functional unit is important. So how do you want to determine your functional unit? How long we own the car, 1 kilometers, or the total distance driven over life of the car. Yeah, we actually use 1 kilometers for our analysis. Right, we base everything based on driving 1 kilometer because it's comparable. Right, because it's comparable. If we are looking at a car, say we use 1 car as a functional unit, what happens is, the lifetime of the car will be different. That's why it makes it not very comparable. But when 1 kilometers of 1 kilometers of driving, it actually gives a better comparison. All right. Next, what should be included in the goal and scope definition is the system boundary. Right. Remember, in system boundary, you define what is start point, what needs to be included, and also what is the end point. So the start point will be the manufacturer of the car. So this is more of we start from the gate, right? And end point is what? End point is the life cycle of the car or lifetime of the car, end of the car. We give an assumption that it's a 200,000 miles or 322,000 kilometers of this car. So this is our assumption, right? And so we know how many miles it's going to drive. right? We're going to calculate that, the results. And also we need to mention what is not included in your analysis, or what is neglected, or what is the limitation of your analysis. So you say the maintenance and repairs are not included because maybe the cars are not very comparable. They are varies a lot, right? And like replacement of the fluids and tires are not included. Also, in this study, excluded the energy use during the car construction, which I think it should not, right? Which I think it should not exclude energy use, because energy use is important to see in this life cycle analysis, right? Maybe the energy consumption in the car construction is a small amount, but this is a very important aspect. It should be included in the life cycle assessment. All right. The next stage is the life cycle inventory. Stage 2 is the life cycle inventory. So basically compile all the informations. Right. We need to know what is the weight of the car, so I know how much material they use. Right. The material we use in the car, we can get it from the GREET database, right, or GREET software, and so from Oregon National Lab, can actually, for a typical car, these are the materials are used, right? What is the percentage of steel, cast iron, or some other materials? And then we're going to look at what about emission factors, right? Emission factor means for a certain material amount or a unit amount of materials, how much emissions actually will be generated. Then we got those emission factors. So for steel, right? For steel, producing 1 kilogram of steel, it actually resulted into 4,972 grams of carbon dioxide equivalent, right? So this is from this emission factor, we can calculate. If I know how much steel I use, then I can use this emission factor to calculate how much emissions generated, right? So this is how you use emission factors to calculate the environmental impact. Well, basically, if you are using some other softwares, it's the same principle or the same logic. Just you probably won't see the emission factors because it's all in that database. All right, so based on that information, you can calculate how much steel GHG emissions and also some other GHG emissions from different materials. Also, you can calculate the fuel efficiency. If you know the fuel efficiency of that, you can calculate the fuel consumptions over the entire product life cycle. So we assume a fuel efficiency is certain mpg, and then how much for 1 liter of fuel, what is the distance it can drive, right? Okay. Well, in this case, now if you know the total length or total distance of the car you can drive, you can calculate how much gasoline will be consumed, right? Because we know this, and then calculate how much gasoline will be consumed per kilometers. All right, so then we get the GHG emission from impact assessment after calculation. So the result will be in this table and this graph. So this you can see the gasoline consumption, right? The GHG emission from gasoline consumption actually composes 91.6% over the entire life cycle of the car, right? So the gasoline comes use because you want to keep the car for maybe 10 years or more, or literally a long time, that it's consumable, right? And next one will be the steel use, right? The steel, the material, mainly the materials for the car, but also some other materials. But you can see the steel and the gasoline are the most two sources of GHG emissions. All right. Next, what we conduct is the interpretation. Interpretation, we evaluate our study, and also trying to find out which variables are the most important or impact on the result, right? And so we identify two parameters, and I'm gonna vary that by the same amount, plus or minus 25%. So the two variables are the vehicle lifetime and also the fuel efficiency. So vehicle lifetime, say we want to reduce the total distance, distance it can drive for this car, and or we want to increase the total distance of the car it can drive by 25%, minus 25% plus 25%. You see these kilometers. And then we're gonna calculate, okay, what is the new life cycle environmental impact or life cycle GHG emissions. Same thing with the fuel efficiency. Every time I only change one, right? If I change the fuel efficiency by 25%, right? Plus, with this fuel efficiency, I'm gonna calculate the GHG emissions. But of course, when we are conducting life cycles, we are conducting sensitivity analysis. If you want to change this one, you're gonna keep all the rest will be the same, right? You'll keep the vehicle lifetime will be the same, right? Will be at the original data, which is this one. All right, so now we can get the result of this sensitivity analysis. You can see, right? This is the baseline from our original study, and this one is when we increase the vehicle's lifetime by 25%. You can see how much GHG emissions can save. This increase means I want to keep the car for a longer time. Then let's look at how much GHG emission can save of their life cycle. Well, it saved a little bit, but probably not a lot. Same thing with if I decrease the vehicle life cycle, means I keep this car a little bit shorter, right? Instead of 10 years, maybe I only keep it like 8 years. In this case, I'm going to look at, okay, how much emission is actually going to increase based on this behavior. It increased a little bit, but it's still not a lot. Compared to what? Compared to the fuel efficiencies. It's the same thing. I'm going to change the fuel efficiency by 25%, right? One is plus 25%, which is more efficient of using the fuel. You can see how much GHG emission actually saved. On the other hand, if you decrease the fuel efficiency by 25%, you can see how much GHG emission actually increase. Right? So from the sensitivity analysis, the fuel efficiency is the most important factor that actually affects the life cycle GHG emission of the car. Right? It makes sense, right? So this is how you use sensitivity analysis to find out the most impactful variables. All right, so after we talk about LCA, then let's look at some other practices, how you can practice sustainability or sustainable manufacturing on the shop floor. And so, let's look at this first. All right, so basically this is you can practice sustainable manufacturing along the entire life cycle, right? From the raw materials, right? Raw material extraction, then preparation of the materials, manufacturing, transportation, right? To the retailers, the use phase, and the end of life. All the stages that you can practice sustainability. For example, in the raw materials, you can think about, okay, instead of using steel, using polymers, plastic, maybe you can use more environmental friendly materials, right? Raw materials, with material preparation, maybe there are some more environmental friendly processes that can make those in the same kind of amount of product. Manufacturing, there are many different ways. I'm going to talk about that now, how to do that on the shop floor. Transportation, same. Truck, airplane, ships, trains, you make comparison and you're trying to look at how can you reduce the GHG emission or fuel use or fuel consumption or GHG emissions by different means of transportation. There are a lot of things you can do. For example, if you're operating the whole a network of transportation, then you can probably use some algorithm trying to find out with what kind of route actually it resulted the least environmental impact, right? Retailers use same thing. You can all practice sustainability in the different stages of the manufacturing or the product life cycle. Well, on the shop floor or within the manufacturing plant, what can you do, right? There are a spectrum of efforts you can use. For example, housekeeping means improvements in the work practice and the maintenance. Make sure it's always clean so you do not have to waste materials, right? You do not have to generate a lot of waste or cause some bufferings because of you have a lot of waste or defects. Well, another one is a process optimization, so which means making adjustments to process to increase efficiency, right? Yeah, reducing cycle time will be one, right? Means it goes through the shop floor very fast. The product goes through the shop floor very fast. It uses less materials, maybe the same materials, but less energy consumption, right? Think about all these fixed inputs, right? The more you use, the more you produce. Actually, the less impact you generate. So also you can probably use some of the different manufacturing processes, right? Or refine your manufacturing process. Instead of using 10 processes, maybe you can use only 2 or 3 processes to generate that same product. These are process optimization. Raw material substitution, same. You can probably gonna shift to some more environmentally friendly raw materials. And new technologies will be, maybe you can use lower resource consumption or waste generation, or use how to figure out if there are some technologies you can reduce emissions from your plant. For example, if you're operating something related to chemical processing, then maybe you can think about how to recycle those kind of chemicals that will be harmful to the environment, right? Or if you have a lot of waste from your scraps or waste materials from making steel or something else, then probably think about how do you make use of those wastes, right? So we can reduce the impact. And lastly is a new product design. Product design actually matters a lot. If you can design a product that use less materials, that'll be great. Then it's gonna affect all the rest of the processes, right? Because some processes will be redundant. You don't have to do those processes. Then that reduces the material. That reduces the environmental impact. So there are many different ways you can practice sustainability in and outside of the manufacturing systems. So this is the one example you can read through and how they use the spectrum of efforts to practice sustainability in manufacturing systems. Process optimization, raw material substitution, just read through it, and also new technologies, right? New product design. All right. Next I want to talk about is a method is called 6R. So when you are, for example, if you are a production manager and you want to practice, sustainability in manufacturing, then you can use the 6R as a guideline, right? Which means recycle, you convert waste into reusable materials. Reuse materials means extend the product life cycle by changing the ownership, right? For example, reuse of the product itself. Recover means retrieve valuable substance from end-of-life materials. Instead of going to landfill, we're gonna recover some most important. For example, the boards, right, from computers, or from electrical boards from computers, or TVs, or many different equipment, right? There are there are actually a lot of very valuable substances, like copper, right? Sometimes even gold. You can recover from these materials. And reduce means we reduce the use. We do not use that kind of material consumption, and reduce the waste and reduce the energy consumptions, right? For example, if you are operating a printing line, or a CNC machine, some studies shows that if you turn on and off of this equipment very frequently, it actually consumes more energy compared to it just keep those equipment or line standby. If you keep it standby, yes, it consumes energy, but it's very low energy. But the time when you turn it on and off, actually that kind of energy consumption is much bigger, right? Much more than the standby energy consumption. So that's something you can think about in order to reduce the waste and the energy consumptions. There are many different ways you have to find out by analysis and by experiment. Same with redesign means we redesign the process, redesign the products, redesign the whole system probably. And remanufacture means some usable parts of the product can be processed to be like new products, inventory, and later used to produce products equivalent or superior to new ones. Right, this is remanufacturing, refurbished, right? Refurbished products. All right. So if you want to practice system manufacturing from the system level, then you can you can look at this this chart, right? First at the operation level, like we discussed before, at the operation level, mainly we are looking at one unit process. Then, for example, the machining process. Okay, you have this milling CNC center, and what are the practices you can do in order to reduce the energy consumption or material use or environmental impact for all these things at a unit level, right? Maybe cleaning, keep the environment, keep the workspace clean, generate less waste. Or you won't turn on and off the machine a lot, or you reduce the standby time, right? Reduce the standby time, or reduce the cycle time. These are all different ways you can do at the unit level. Well, at the shop floor level, then you probably can look at the scheduling problem, the layout plan, so that if you change the layout, you probably won't be using a lot of transportation distance, right? The transportation will be a lot reduced. In this case, you use less energy, right? So that's how you can use the layout to reduce the environmental impact. Same with scheduling, right? So if you schedule the work that result in less transportation from each other, then it reduces the environmental impact. If you schedule it to reduce the cycle time, same thing, it reduces the environmental impact. It's all related. And also on the shop floor, you can look at the whole manufacturing plant. Like if some of the places there's no production at certain hours, then you probably just turn off the light, so you don't waste those kind of energy, right? And so that's the different ways you can practice shop floor level of sustainability. Well, at the enterprise level, then you can start to make some strategies, some policies, and then try to find out how can you practice sustainability at the whole enterprise level. Then lastly, we're going to look at social sustainability. So social sustainability is also a very important factor in manufacturing or in sustainable manufacturing, because there are increasing social concerns that, especially from the public, related to to either employees' psychological health or physical health in manufacturing companies, but social sustainability is not just that. Social sustainability, it has a lot of other metrics or aspects. Today we're going to look at what are included. If you have heard about the company Foxconn is a company that is making iPhones or iPads, but also a lot of other products that you probably use every day, and they operate those companies or assembling factories in Asian countries. And there was a time that because they the workers are working all the time and do not have a lot of rest, also a bunch of other policies that people are under really great pressure. So some suicides happened, and then there was a time that Foxconn was under a lot of pressure from the public. Of course, later it improved, but this is how social sustainability actually matters in a company, because it's really going to affect your business eventually. Right? If you remember Charlie Chaplin's movie about working on a production line, so a lot of times people just use you as a tool, right, or as a machine, and just repeat all the same same operation, or even the same gesture all the time, and make you your life got bored, and you're bored, and you think there's not much meaningless of your work, and especially if you do not get a lot of pay, then you got a lot of pressure. So that's social concerns. Some of the social concern aspects in within the manufacturing systems. So in general, when I talk about social responsibility, it's really the corporate social responsibility. It's a concept, whereby companies integrate social and environmental concerns in their business operations, in their interaction with the stakeholders on a voluntary basis. And there are many different ways you can look at, there are different dimensions of social responsibility. For example, if it is from a larger perspective, right? UNEP, United Nations, actually give a framework how you can evaluate the corporate social responsibility in your company. For example, you're going to look at workers. These are the what stakeholders. Workers, what are the social concerns, right? Psychological, physical health, their rights, right? Their human rights, or their compensation, they are all preserved, right? And so these are some of the metrics related to the workers. When you're talking about consumers, we're gonna look at if your products actually gonna have some potential harm to your customers, or if your products have something that is not respectable to your customers. So these all something that related to the second stakeholder is the customers. And then also local community. So if you operate your manufacturing plant in a place, then you might want to think about how can you benefit the local community, right? And either by employing local employees, or you can help local business, right? You can generate more business opportunities, or some outreach, more education, all these kind of different things you can do for the local community. Same with society. Let's think about the whole society, how like Apple or Microsoft, how they changed the way people behave in the past decades. Also all the other different actors along the value chain, right? Along the value chain. And so there's one initiative called GRI. So GRI is called Global Reporting Initiatives. It provides a guideline for companies who want to report their social sustainability, right? So they will include the 4 different categories: like labor practices, human rights, sincerity, and also product responsibility. So you can use those in 4 aspects to provide to talk about your social sustainability or measure your sustainability. And another one is so dimensions of sustainability. When we're talking about workers, especially on the shop floor, how do you measure all these sort of impact, right? So United Nations gave us social impact categories of all these categories. It includes freedom of association, right? Child labor, fair salary, working hours, forced labor, equal opportunities, health, safety, and social benefits. You can use all these different impact categories to evaluate how your company does in each of the categories, right? And also there's a 12 dimensions. So 12 dimensions is the one study I did with another colleague years ago, that we developed those kind of 12 dimensions, trying to measure the psychological, especially psychological, social sustainability in organizations. So more focusing on the worker itself, all right, or more focusing on the worker on the shop floor. It includes the compensations, the physical and mental safety, the demand, right? You demand more if the company provide what can meet your demand, right? How much, and also variety of tasks and rules. Remember, we are talking about the cellular manufacturing, right? If you can do a variety of different tasks, actually, you're not getting too bored, or you can feel that kind of satisfaction. Social interactions, you can talk to others, you can discuss. These kind of social interactions are some of the demands you need to have with workers. Also, the growth of skills and of knowledge and opportunities for accomplishments and status. Value of the work, thinking of if your work has value or not. Also, it's got autonomy. How much autonomy you can have in your work or in your job. And also the growth and personal development. So these are the 12 dimensions we developed, trying to measure the social sustainability on the worker perspective. All right, so that's pretty much all for this lecture, and also for this course. And some of the takeaways about this class it includes the theory. You need to understand the true bottom line, the master equations. Understand what is life cycle thinking, and also understand what is the system, how system thinking is defined. And also when you're talking about practice in manufacturing, the most important one, the LCA. You need to understand how to do the LCA. You later probably be asked to do a separate LCA study on a product or a process or the system, right? The four different stages. Goal and scope definition, life cycle inventory, impact assessment, and interpretation, right? 6R, and also a spectrum of efforts on that. How do you practice sustainability on the shop floor? I didn't list it here, but that's in the lecture. And lastly, the social sustainability, the dimensions of social sustainability and different metrics, what kind of stakeholders, and for different, different guidelines, how do they define social sustainability, how do they measure sustainability? All right, so that's all.